So the first lecture will be rigidity modulus of thrust, which is yesterday I talked to about Young's modulus. Today I am going to talk about rigidity modulus. How do you define rigidity modulus? Suppose you take a rectangular specimen A, B, C, D. You apply a tangential force parallel to the top and a force in the opposite direction at the bottom. So you have a tangential force at the top and an equal and opposite tangential force at the bottom. Then this rectangular face ABCD will become a parallelogram ABC'. That is, this face will move in the directional force by a small amount, and therefore this angle, which is 90 degrees, will become less than 90 degrees. So AC, which was perpendicular to AB, moves to AC dash. The angle C dash is a small angle. Few minutes, that angle phi is called the shear strain, provided the shear strain is the distance moved CC dash by CA. CC dash by CA will be tangent of the angle phi. And tangent of the angle phi for small values of phi is equal to phi in radians. So the angle phi will be equal to CC dash by CA. This is called the shear strain. Now you are applying a force on the area CDEF. So you find out what is the force divided by the area. That is called the shear stress. So the rigidity modulus is shear stress, the shear stress by shear strain. This is called the rigidity modulus. The rigidity modulus will always be less than the X modulus, less than 50% of the X modulus. Because there are relations connecting the X modulus and the rigidity modulus and the Poisson's ratio, the X modulus, bulk modulus and Poisson's ratio. You will see that the maximum value of the Poisson ratio, the maximum value of the Poisson's ratio must be 0.5. If it is more than 0.5, then your bulk modulus will become negative. If y is positive, bulk modulus will become negative. That means you compress, the volume will increase. And this is an unstable situation. So the Poisson's ratio of any material must be less than 0.5. It is a positive number, less than 0.5. It is between 0 and 0.5. So 2 into 1 plus sigma. 2 into 1 plus sigma is greater than 2. So n will be y divided by a number greater than 2. So the rigidity modulus will be less than 50% of the X modulus. For the same material, if you use two different materials, you can't use this relation. Now I am going to measure the rigidity modulus of a circular wire like this. So what do? I take this circular wire, I clamp it at the top and I attach a disc and then I twist the disc. Okay. So I take a wire which is clamped at the top. The wire has a length L and a radius A. So I take this wire, it is clamped at the top, and the bottom I twist it through an angle theta, small angle theta. So I take a cylinder of radius r less than 8. The diameter, the radius of the wire is 8. I take a cylinder within the wire of radius r less than 8. That is the cylinder I have shown here. This cylinder has a radius smaller, which is OB, which is less than the radius of the wire. When I don't twist, AB is a vertical line, and I have not twisted. Now I twist the bottom. When I twist, this is clamped. So when I twist the bottom, A does not move, but B will move to the position B dash along the circle. Twist means you are not increasing the radius, you are changing the direction of the vector. So the vector OB will change to the position OB dash. So B will come to B dash, and the line which was AB originally will now become AB dash. And this angle BAB dash is our shear strain phi. So the angle BAB dash is my shear strain. I must relate the shear strain to the angle of twist I have given. What is the angle of twist? BOB dash is the angle of twist. I have taken the radius OB and twisted it to the position OB dash. So BOB dash is the twist I have given here. I must relate it to the shear strain phi. So if phi and theta are small, the displacement dP dash is the radius r multiplied by angle of twist. R into theta is B dash. It is also equal to AB into phi, the angle, the shear strain. AB is the length of the wire, so L into phi must be equal to R into theta. Therefore, phi, the shear strain at a radius R is R by L into theta. I given twist theta, the shear strain is not the same at all radii less than A. It depends on the radius. If you take R equal to 0, no shear strain, because that point does not move when I twist. If you come away from O, then the point moves. How much it moves depends on R. So the shear strain is proportional to R, and it is related to the angle of twist and the length by R by L into theta. Now I take in this is my radius A of the wire. I am taking a circle of radius R and a circle of radius dr. R plus dr. I take two concentric circles R and R plus dr. I take two angles. This angle is psi and this angle is psi plus d psi. So the two vectors OC and OD. OC is at an angle psi, OD is at an angle psi plus d psi. It the polar coordinates I am using. I take the area on this angular ring between psi and psi plus d psi. What is the area of the shaded figure? It is BC will be equal to R d psi. And the width that is strip is dr. So area of the strip is width into the length, that is r dr. So on this strip there is a shear force acting because I have twisted the wire. So what is the shear force? The shear force may be a force like this. It will be tangential to the surface. You saw that the shear force is tangential to the surface and it will be normal to the radius vector r. So I calculate for a given shear strain phi, what is the shear force acting on this area? So the shear force dF on the elemental area is the stress. The stress is rigidity modulus into phi. The strain is phi, stress by strain is n, so stress is at phi. Stress is force per unit area. So force on this area is n phi into r dr d psi. So that is the force on this area. Now I take this force and find out what is the couple of this force above the axis. This is the axis of the wire. I have to apply a couple to twist it. So what is the couple due to the force dF above the axis of the wire? That will be dF into the distance r. So the couple DC will be the force n phi r dr d psi into r. This is the couple due to the force on the area dr into r d psi at a distance r from the center and between psi and psi plus d psi. I now substitute for phi. Phi is r theta by L. So in terms of the twist, n r theta by L r dr d psi into r. So the term n theta by L, that is a constant. Theta doesn't depend on r. When I twist through an angle theta, every element, every radius vector changes by theta. So I take n theta by L outside, then collect all r values. There is r here, r here, r here. So it is r cube dr d psi. Now I have to integrate to find the total couple. I have to integrate over psi from 0 to 2 pi, r from 0 to d. So when I integrate d psi from 0 to 2 pi, I will get a factor 2 pi. R cube dr, I integrate 0 to a, I will get a to the power of 4 by 4. So if you put all that, then the total couple I must apply to twist this and through an angle theta is pi n to the power of 4 by 2l into theta. So this is the couple I must apply to twist the wire at this end through an angle theta. Now I twist the wire and let it go. Then it will execute oscillations. I have a disc at the end of the wire. So this disc has a moment of inertia, and this disc will execute torsional oscillations. So the equation is I d square theta by dt square plus C must be 0. Now in my experiment, normally you hang a wire from the ceiling, you have a very large weight, you twist it, you have a mirror and you measure the period. It will be very slow oscillation because the length is very large and your moment of inertia you put a large weight that is also large. It is difficult to change the length when you are hanging it from the ceiling. So I made a tabletop model where you can change the length and see the effect of the length. So here you have the wire and I have a small disc of moment of some mass which is fixed at the center of the wire. So the wire extends from here to here. I want to change the length of the oscillating portion. So I have two bars here. I can loosen this screw, I can loosen this nut, move it up and down, clamp it, this screw and this screw. Then this point will not move. So the length becomes this. But I have two symmetric portions. There is the second portion of the wire. Now, this also I move so that the two lengths are equal. Then when I twist it, there is a couple due to this length of the wire plus couple due to this length of the wire. Both are of equal length. Therefore, the couple now must be multiplied by a factor 2. I have to multiply the couple by a factor 2. The L is the length from this point to this point. So this is the equation. Now put theta is theta naught e power I omega t. You will get the frequency of vibration. So the frequency omega square will be equal to 2 into pi n power 4 by 2n divided by I. 2 and 2 will cancel. Omega is 2 pi m. So omega square is 2 pi m whole square will be 2 into pi n power 4 by 2l into moment of inertia. This is L. I put L in a script, but it has come as a symbol, as an ordinary category. So this is L and this is I. So your frequency is 1.25 pi n power 4, 2 and 2 cancel by L divided by power half, square root of that. So this will be the frequency of oscillation of this wire as I change the length. Now you can see that the frequency is inversely proportional to the square root of the length. It is proportional to 1 by square root of L. The frequency is directly proportional to the square of the radius of the wire. A power 4 square root. That means if you make the radius double, frequency will go 4 times. And it is inversely proportional to the square root of the moment of inertia. To increase the moment of inertia, frequency will come down. So you can have here, the setup is this, which you can use on a tabletop. And you see that wire has a diameter about 7.7 mm. Okay. I have to choose the diameter and the moment of inertia so that with a wire about 50 centimeters long, I can change the length and get the frequency in my range of my signal generator, 20 to 100 Hz. So, the diameter of the wire is about 0.7 millimeter. And I have chosen a brass disc of a suitable dimension so that the moment of inertia is such that the frequency will be inversely proportional to I. I must reduce I to increase the frequency. So my disc is very small. It is a disc about 3 something like 5 centimeter across, half a centimeter in thickness brass disc. And to know the mass of the disc, you can calculate the moment of inertia. It is mass into radius square by 2. So I know the dimension of the disc, I know the density of gas, so I can calculate the mass and I can calculate the moment of inertia. But to make it twist, I have to attach 2 rods to which I have fixed small magnets. These are 2 coils. So the current goes through the 2 coils in series. This coil will push this magnet this way, and this coil will push this magnet this way. So you get a torque. So you get a twisting force. But if I have large magnets, I must add the moment of inertia due to the magnets also. So I must know the mass of the magnet and the distance of the magnet from the center of the disk. So it will be m into d square plus m into d square. So you must add the moment of inertia of the disk, capital M r square by 2 plus 2 small m d square. Small m is the mass of the magnet, d is the distance of the magnet from the center of the wire. So that gives you the moment of inertia. You can change the length from 20 centimeters to 5 centimeters. You can move it. That means you are changing the length by a factor of 4. So the frequency will increase by a factor of 2. So you start with the frequency 20 Hz, you will end up with the frequency 40 Hz as you reduce the length. And you can measure these frequencies quite accurately with my signal generator. Frequency is very stable. So all I have to do is, I have to move this to 20 centimeters, fix it at the back, and fix these 2 screws tight. Similarly, I have to move it 20 centimeters from here, fix it at the back, and fix the 2 screws. I take the power cable, connect it to the output of my power amplifier. The input is connected to the signal generator. I give some voltage at the signal generator, 2 volts, and I change the frequency. I again start with the high frequency and I lower the frequency. Then you will see that these will start oscillating back and forth, and at resonance the amplitude will be maximum. So find out where you get the maximum amplitude and note that frequency. Then I change the length, repeat the experiment. So change the length by 2 centimeters. Let us start and then repeat the measurement of the frequency. If you want to show how the frequency changes with the moment of inertia, make a similar brass disc with with a slot. You can put it at this disk that will increase the moment of inertia and the frequency will come down. So the student can verify how the frequency changes with length, how the frequency changes with the moment of inertia. And the whole setup we put on a table down and you can measure the frequency very exactly. So I have given the data. I don't think you can see from there. I have given the density of brass 8,500 kilograms per meter cube. I have given the diameter of the brass wire 1.5 in millimeter. Therefore, radius is 0.75 millimeter. Moment of inertia of the disk, the mass square by 2. I know the mass. I have given distance between the magnet 2D, that is 7 centimeters. So you can calculate D is 7 by 2. Mass of each magnet I have given, that is 2 grams. When I made the first setup, the magnets were heavy, but in this setup, the magnets are light. So the mass of the magnet is given here. It is 0.6 grams now. We have to calculate moment of inertia due to this mass. Don't take the value you have given in the case. Then I have kept length at 17.5 50 up to 5. Frequency changes from 80 to about 41. And then I plot square of the frequency against 1 by length, and you get a straight line to find what is the slope, and then you can calculate the X modulus. The rigidity modulus is 4 pi times the moment of inertia divided by 4th power of the radian into the slope. So you measure the slope, you know all other quantity, calculate the moment of inertia. And I get a value 4.05 10 to the power of 10 pascals and 40 GPa. The X modulus will be 100 GPa. So the rigidity modulus is 1 by 2.5 times the X modulus. But please note, brass is a name we give to an alloy of copper with zinc. You can vary zinc over a wide range. All of them are called brasses. So you buy a wire in the market, you buy a sheet, they won't have the same composition. They are called brass, but they are not the same material because amount of zinc will be different. So from this rigidity modulus and the X modulus at the bar, you can calculate some Poisson's ratio, but it won't be correct because the measurement is not based on the same material. Brass is a name given to a wide range, alloys with a wide range of composition. So this is how to determine the X modulus. There is a much, in my opinion, much more convenient setup than what you have in your, and you can verify how the frequency varies with L and with I. So any questions? It's a very simple experiment. Any questions?
Can you check the quality of brass?
I don't hear that completely.
Can you check the quality of brass by using the modulus?
See, okay. If you want to test the quality of brass, you must first take brass with different known compositions. Say zinc 20%, 25%, 30%. You must measure the rigidity modulus for these different. Then you can test it. But to you go to the market and tell the fellow, give me 30% zinc, you will be lost. You ask brass, it will give you 30% zinc. The company will not tell him what is the composition. You have to go to a company which makes copper and copper alloy and ask them to supply wire of different composition. But that will be costly because you need only small length and wire and the company will sell very large lengths. So this would not be a very convenient way for measuring the composition. It's possible, but not convenient. So I think after I go to the workshop that we are